Again, today we're talking about ACPA design apps, both Compare Flow and PipePac. And today our speakers, we have Corey Frazier. Corey is our Northwest State Director. Corey graduated from the University of Texas at Arlington. Apparently he loves dogs and pizza, so that's pretty awesome. And Corey does have over 10 years of experience in the pipe industry, so very knowledgeable, and looking forward to what he has to share with us today. Also, we have Trig Hoff. Trig is our Northeast, so we have both sides of the country represented today. Northeast Region Engineer. Trig went to Ohio State University. He enjoys paddleboarding, skiing, and carpentry, so very outdoorsy kind of guy. And he has 8 years of experience in our industry. So both very knowledgeable, and we'll be able to share some good tips for us to take away from this training. So Trig, I'll go ahead and turn it over to you. Thanks everyone for joining us. Trig?
Great, thanks Kim. I do want to point out with this photo on the right, it's not super flattering, but just seconds before that, I was doing just fine on the paddleboard, and my wife just happened to catch the perfect timing on the second shot. But okay, so let's kick this off. I'm gonna cover Compare Flow. That's our app available on the Google Store, as well as with Apple, whatever the Apple equivalent is. I don't have an Apple phone, but so you can download this app. Please feel free to do so. It is free. So let's check it out. Let's see how it works. So when you open the app, this is the first screen that you're going to come to. We've got 3 options on this first screen. At the bottom of the page is a link to our website. So you can go to the website. There's a lot of design information in there. Pipe design, inspection, installation techniques, boxes, pipes, all sorts of information on our website. So please check that out. On the link above that, it will take you to a window that describes about the ACPA, as well as describing the Manning's formula that we're using in the application. So that gives you a little rundown on how the app performs. Also, one of the keys to the Manning's equation is the roughness coefficient. This section describes where those values for the end values come from. Those are from the FHWA 2012 design manual. And then at the top of the app, the top option here, this is a link into the real body of the app. So let's press that and follow it through. So when you press that, it's going to take us to the flow capacities for different types of pipe. And what you can see here on our main screen, we have 5 different options. So when you're using this flow comparison, you can check up to 5 different types of materials to see their flow capacities. So it defaults to concrete pipe at the top, then elliptical, then arch, then precast, box culverts, and then flexible products is below that. And we're going to briefly touch on each of those, but let's step through looking at the concrete pipe. But before we get into that, I want to do a sidebar on flow, since we are comparing flow here. And we're going to launch a poll just to kind of get a feel from everybody and see what level of understanding we all have about flow. So what I'd like to know is, what day of the year do you think results in the maximum sewer flow over a 15-minute period? So Kim, if you could launch that poll for me.
Okay, yeah, the poll has been launched. People are starting to answer that. Now, I have heard in the past webinars, people will say they cannot click on the poll. If you're having problems with that, either minimize or maximize your screen and try again. I've heard that is a good fix. So make it not full screen, and you should be able to click on that. We've got 75% of the folks who have joined us today have voted. We'll give them maybe just another second or two. Okay, I'm going to close that and share the results. So Trig, since you're the presenter, you can't see that, but 73% said the Super Bowl. We had 5 with the 4th of July, 19% with Thanksgiving, and 3% said Christmas.
Interesting. All right. Well, thanks again. So that would actually be, if I hadn't already heard the answer, I would have probably jumped on board with either Thanksgiving or the 4th of July. However, I think a lot of us have heard this answer maybe back in school. It is actually the Super Bowl. Super Bowl Sunday tends to be the peak flow for most municipal treatment plants. This is an example from 2013 from the Hampton Roads Sewer District in Virginia. So the dashed line shows our typical Sunday, and then the red line shows Super Bowl Sunday, and this was from 2013. So the trend is relatively similar, but there are a couple differences. Kickoff is at 6:30, so the runs to the restroom are going to slow down around that point. And then we get a little boost at halftime, so people are making another run to the bathroom. Interestingly enough, it's not as big a boost as you might expect, because obviously you're watching the Super Bowl for the advertisements, so people are going to stick around for that. And then at the end of the game, we notice, the bathroom visits are dropping down, but then we get a little boost again right after the game is complete. So it's kind of an interesting trend line there of how America uses the toilet on Super Bowl Sunday. So, okay, back to the app. So we're zoomed in here on that first page of the app. These are the top two options. So what we're seeing is the type of pipe, and then where it says not chosen, we're going to select a size for that type of pipe. Then we can see the barrel option, so it tells us how many barrels we're designing for. And then the flow right now is showing 0 cubic feet per second, but that's obviously going to change as we make our selections. So we click on our pipe type, and that brings up a drop-down menu, and we can now choose, which one of those 5 types that we'd like to choose. So it could be concrete pipe, it can be elliptical, it could be arch, precast box culvert, or flexible. So we'll choose concrete pipe. And now to advance into the next stage, we choose the button on the right-hand side. We click that. That takes us to the real design aspect of this application. So let's walk through that real quickly. At the top of the page is going to show us the pipe material that we chose. So if you meant to choose box culvert and it's showing concrete pipe at the top, now you know you need to go back and make a different selection. So just keep an eye on the top of the page. Below that is our diagram, and obviously with a round pipe that doesn't really show us a whole lot. This will really come into play when we're looking at an elliptical, an arch pipe, or a box culvert. Then the diagram is a little bit more in depth. And below the diagram is our user input. So this is where we do all of our calculations. At the top of the user input section, we can either choose US units or SI. We're going to stick with US today, but the SI is still an option, and that will obviously change all the calculations in the output. And the next decision needs to be what roughness coefficient we're going to use. So we can click on the question mark here, and that will bring up the roughness coefficient description. You'll notice that there are several different coefficients listed below, but before we get into that, we're going to run another poll, and I'd like to know what your thoughts are in terms of what Manning's End should we use when designing for plastic pipe. And so we've got some different options here. Kim, if you could launch that poll, please.
You bet. So poll is launched. Again, your options, we're trying to find out what you think corrugated plastic pipe should be designed to. Your options are 0.01, 0.02, 0.010, 0.010, 0.012, 0.015, and 0.018. And as you'll note in the question, RCP typically uses 0.012. Okay, we've gotten close to 80% of folks have voted. So I'm going to go ahead and close that. And interestingly, we have a very even spread of thoughts here. So Trig, we have 27% said 0.010, 23% said 0.012, 24% said 0.015, and 25% 0.018.
Interesting. That is quite. I mean, that's a pretty even split 4 ways. Okay. Well, we have some guidance in the app that would give you some guidance in terms of what to choose for plastic pipe, and you can see that if you click on the question mark like we just did, you'll see the range that comes up. Also, if you have chosen a flexible pipe, so right now in this example we're looking at concrete pipe. If you had chosen flexible pipe, when you click on the roughness coefficient, you get an additional menu, drop-down menu that lets you choose which type of material you're using. So if you were, say, going to design for an HDPE or polypropylene pipe, you would want to, theoretically, certainly I would as a professional engineer, want to design for any potential corrugation growth inside that pipe barrel. You could choose corrugated metal, you could choose spiral rib metal, profile wall PVC, solid wall PVC, all the way down the line. If you choose, so about a quarter of you said that you wanted to design with a 0.010, then you would choose user defined. You would type in 0.010. Typically, in most states, so I cover the Northeast, most of my states, the Manning's End for plastic pipe is going to be in the same range or possibly the same point as concrete pipe. And I just want to take a sidebar here to discuss that a little bit. So this is the FHWA design manual, design guide for highway culverts from 2012. And it gives table B1 with Manning's End values for culverts. So you can see concrete pipe here has a range of 0.01 to 0.011. Here's corrugated metal, anywhere from 0.011 to 0.023. And with corrugated polyethylene, it has a range from 0.009 up to 0.015. PVC is in a similar range of 0.009 to 0.011. So all of these values that we're showing, FHWA is showing in that table, these are laboratory values. We need to take that into consideration when we're designing pipe. So those lab values were researched using clean water, using straight pipe without any bends, no manholes, no debris in the pipeline. So certain things that we need to account for when we're designing the pipeline. But the biggest difference between the different Manning's End or the roughness coefficients are the differences between a smooth pipe and a rough pipe. Now, when I say smooth and rough, I'm not talking about the smoothness of glass versus the roughness of a burlap sack. That's not the comparison we're concerned with when we're talking Manning's End. We're looking at the difference between a straight wall and a corrugated wall. That's where we really build up that turbulence and it constricts the flow. So keep that in mind as well. With concrete pipe, our lab values are typically a 0.01 and a 0.011. But because all of those things we just mentioned, the fact that we're not designing for clean water, we're not designing without any bends in the pipeline, we assume there's going to be some manholes, there's more than likely going to be some debris in the pipe, we need to incorporate some factors of safety. And typically, historically, engineers incorporate a 20 to 30% factor of safety. So for concrete pipe, we would recommend a 0.012 and a 0.013. So there's that 20 to 30% factor of safety in there. Typically, again, most of the states that I work with from a DOT standpoint, they choose to use a 0.012 as their Manning's End. There are a few outliers that will do a 0.013, but again, that comes up to the designer to choose. Now, I want to give you a few shots of the different pipes that are what they look like on the inside. So we just talked about how it's not necessarily the smoothness, what we normally every day talk about smoothness. That's not exactly what we're looking at. What we're looking at is the straightness of the wall. So if you look down this concrete pipe barrel, you'll see that the wall is straight. And there are still joints in there. There's still some fluctuation in the total run of this concrete pipe. This piece of pipe has been in the ground for about 80 years. So there is a little bit of fluctuation. It's not a perfectly straight installation, but that's all taken into account, and that's 20 to 30% factor of safety. So here's an example of a freshly installed box culvert job. Again, you can see that those lines, that wall is nice and straight. It's going to have a really good Manning's end. This is also going to be in that 0.012 range, just like the concrete pipe. Now, this is a picture of corrugated metal pipe, and yes, this is in really bad condition, but let's just for a second, let's focus on the top half of this pipe. So you can see that we have corrugations in there. The water is going to hit each of those little corrugations. It's going to build some turbulence, and we are going to constrict flow just with a standard corrugated metal pipe. Now, this specific pipe that we're showing is also illustrating a couple other things. First of all, we can see exactly where the flow line was on this pipe because that's where it's rested. The other thing is that this pipe, and you can see there's a sandbag in a couple sandbags in this line. This pipe, the invert had started to rust out. And so from a design standpoint, again, when we're concerned with the resiliency of the hydraulic capacity of these pipes, we want to make sure that we're taking all of those future changes into consideration. So with the concrete pipe, we need to consider the entire length of the design life. With the metal pipe, the same thing is true. So if that flow line is going to become rusted or completely missing, that's going to change all of those flow capacities. All right. So now let's look at a plastic pipe example. This is a piece of polypropylene. This is a 48-inch pipe. It's the same diameter actually as the CMP we just looked at. You'll see a lot of similarities, with the exception of the rust, between the inside bore of this pipe. This is a triple wall pipe. It's installed a few miles from my house. It's got a couple feet of cover and an ADT of less than 500, I would assume. You can see that there are some corrugations growing in this pipe. It's been in the ground for about 10 years. On a 48-inch pipe, these corrugations that are starting to show up on the smooth inner liner are probably anywhere from a 1/4 inch to a 1/2 inch deep. So that corrugation is going to impact the flow of this pipeline. So as a designer, I would probably put this above the concrete Manning's end. So if concrete's at 0.012, I certainly would not design this pipe for anything less than a 0.015. I might even trend a little bit closer to the CMP, maybe that 0.018. Okay, just a quick recap of those ranges of the different types of materials. Again, these are ranges and they're lab values, so we need to take that into account. So if the lab value for corrugated polyethylene with a supposedly smooth wall is up to 0.015, well, as it grows corrugations, we want to probably take that 20 to 30% factor and apply it to the 0.015. That's where that 0.018 is coming. A little bit more detail on the corrugation growth. I'm actually not going to get into that too much. Happy to answer any questions you have about it, but let's keep moving with the app. Just one more shot of corrugation growth. So let's move on with the app. User input, we choose our pipe diameter, we click on that diameter and it gives us a drop down. Now we can scroll through all of the available sizes for the concrete pipe that we're designing. Let's say we choose a 36-inch. The next step is going to be choosing the pipe slope for this installation. So you would click in that box and then you can choose what your pipe slope is going to be. This is in a percentage. So right now what we're showing is a 0.1% slope. So 1/1000th of a foot per foot of length. Okay, and now we choose our flow depth. And we have two options here, so we're showing two different screens. First of all, you can click in the numerical entry box, and then we'll have the little keypad pop up, and you can choose 80% flow depth. Or the other option would be to use the slider bar. So it defaults to 100, and now we can slide it over to whatever we want it to be. So if it's 80, we can slide it to 80. If you're assuming that your pipe's going to flow at 85%, we can type in 85, or we can type in 80 and slide it to 85. So this is it's really whatever you're comfortable with when you're using the app. Okay, so below the input, we have our results section. So this is going to show what the pipe flow is, what the area of flow is and the velocity of flow. So that area of flow, remember, is not going to be the area of the pipe. It's the area of flow within the pipe, because we may not choose 100% full pipe. All right. When we click on the button on the left-hand side, that brings us back to the comparison page. And we have now completed the comparison for the concrete pipe, and we can do the other 4 sections. Like I said, we can do up to 5 comparisons. You can mix and match. It can be reinforced concrete pipe versus reinforced concrete pipe. So maybe you want to consider a double barrel versus a single barrel. Maybe you want to compare different sizes of pipe. You can also check out concrete pipe versus elliptical. So maybe you have limited fill height. So you'd go with an elliptical and you want to see what size elliptical corresponds to a certain size of concrete pipe. We can compare pipe with box. We can compare concrete pipe with plastic pipe like we just showed. We can compare it to metal pipe. You get the idea. We have a lot of different options here. So with that, I am going to launch an example video. So we put together the video here so that we can show how the app works with a little bit of a voiceover. All right, here we go.
In this example, the design engineer is planning a pipe installation utilizing 2 side-by-side polypropylene plastic pipes, each with a diameter of 48 inches. Let's look at how compare flow could be used to check the relative capacities of other pipe options. The first step will be to open the compare flow app. On the first screen, we're provided an introduction to the ACPA and the application. Let's click on the orange arrow in the bottom right-hand corner to advance. Now we have 3 options: the flow capacities, an about page, and a link to the American Concrete Pipe Association website. We'll choose the flow capacities, which brings us into the flow capacities page. As we mentioned, our hypothetical design engineer is planning a twin 48-inch polypropylene storm sewer, and they would like to consider some other options. So let's start by inputting the twin polypropylene pipeline. The first selection will be the pipe material. We choose the drop-down and select circular flexible pipe. This brings us to the circular flexible pipe page. At the top of the page is our diagram, in the middle is the user input, and at the bottom we will show our results. First selection will be our roughness coefficient. When we select the roughness coefficient box, it gives us several different preset options for flexible values. Because we're looking at the potential for corrugation growth, let's choose 0.018. Then we set our pipe diameter. As we said, the engineer is considering twin 48-inch pipes. So we scroll down, we choose 48 inches, and we can set our pipe slope. We will assume a pipe slope of 0.2 and a flow depth of 100%. So this pipe will be designed for full flow. When we hit the next key, we see our result for this single run of 48-inch pipe at the bottom of the page. But remember, the design engineer was planning a double run. So we hit our back button at the bottom left. This brings us back to the flow capacities, and we can choose 2 barrels rather than 1. That gives us a flow of 92.79 cubic feet per second. Now let's look at some other options. Perhaps the designer would like to consider corrugated metal pipe as an option. So again, we come into our material selection, we choose circular flexible pipe. Remember, plastic pipe and metal pipe are both flexible. Choose our coefficient. Corrugated metal has a coefficient of roughness of 0.022. So we'll choose that. In the pipe diameter section, let's assume a 60-inch pipe as a replacement for the twin 48s. Our pipe slope, again, was 0.2, and we're designing for full flow. We hit next, and the pipe flow is given at the bottom of the page. When we hit the back button, or the left-hand arrow, it will show us what a single barrel of CMP 60-inch diameter offers. So our flow rate, twin plastic barrels, is 92.79. Our flow rate for the single corrugated metal 60-inch is 68.83. Clearly that's not an option. Let's check what would happen if we were to use that same size, 60 inches of concrete pipe. So we select our material. At the top of the page is circular concrete pipe. Our roughness coefficient will remain at 0.012. Our pipe diameter, as we mentioned, we're going to try a 60-inch. Pipe slope is 0.2, and we're designing for full flow. We hit next, and our result is at the bottom of the page. We hit the left arrow at the bottom. That brings us back to our flow capacities. And now we can compare the top three options. We have the twin 48-inch polypropylene. We have the single 60-inch CMP. We have a single 60-inch reinforced concrete pipe. So now we can compare the top three options, and concrete pipe results in the largest flow capacity. Let's go ahead and check elliptical pipe. So we'll choose elliptical concrete pipe. Our roughness coefficient again will be 0.012. And for a pipe diameter, as you can see, we show equivalent diameters for a round pipe on the left, and then the rise and span of the elliptical pipe on the right. So let's choose, say, a 60-inch equivalent pipe. So that would be a 48-inch by 76-inch. Our pipe slope will be the same, so we'll choose the 0.2. Flow depth of 100%. We get our result, and we hit the left arrow at the bottom of the page. That brings us back to our flow capacities, where we can compare all 5 of the different materials. Now, what's interesting about this elliptical pipe, if you notice at the bottom, it's a 60-inch equivalent with a 48-inch rise and a 76-inch span. So that 48-inch rise is the same as the twin barrel polypropylene. Those were 48-inch pipes. So we have the same amount of cover requirement with that 48-inch rise of the elliptical, but by having the 76-inch span, we've accomplished much more flow capacity with 130.56 cubic feet per second. So that's the beauty of the elliptical pipe.
All right, now we're going to transfer presenters over to Corey, and he's going to cover PipePac.
All right, thanks, Trig.
Can you guys hear me okay, Corey?
Yes.
Okay, I was just saying before we moved over to you, Corey, that I did have a couple of questions that were typed in, wondering where to get the app that Trig just covered and what formats it was in. So you can get that on both the Android and the Apple stores. It is not available as a Windows file. So it is currently only available as an app. And it's called Compare Flow as one word. So if you're looking for that, that's where you can find it. Okay, turn it over to you, Corey.
Great. Okay. Just a second. Okay, thanks, Trig. So now we're going to switch gears a little bit and move towards our PipePac, which is a web-based software. So pipepac.org is where you can find this application. Oh, sorry, just a second. Having some issues moving forward.
Just while Corey's fixing his technical difficulties, I was just going to mention the one Corey is working on or about to share with us is at pipepac.org. It is not an app to be found on the Android or Apple store. So this one is only a desktop application. So go ahead, Corey. Looks like you got it fixed.
Yeah, great point. So PipePac is a web-based application. You do need internet connection to run it. It can be found at pipepac.org. So this was a joint venture between both the US producers and Canadian producers. It's available in both metric and US customary units. If you are outside of the US or Canada, you do have the option to customize some of the inputs. So you could put in different loading criteria for what you need. Now, if you notice, there is 3 different options going around the horn of the PipePac logo. We have the LCA, cape, and 3-edge bearing. If we take a closer look at what each of these do, we basically have a holistic approach to both specifying, designing, and looking at your future costs and life cycle analysis. So the 3-edge bearing analysis option is a way for us to design a class of pipe based off certain installation criteria. So we can take a look at the soil structure interaction for a complete pipe design. Now, the cost analysis of pipe envelope takes a look at the entire cost of that system. So you're not only looking at capital costs of the pipe itself, but you're also looking at material costs, trench width, trench depth, and length of pipe. It also includes labor and some other different costs associated. And then finally, life cycle analysis is where we can take a look at future costs, maintenance costs, and some of the other costs associated over the entire lifetime of that project. So one of the things that PipePac helps us do is take a holistic approach and really identify a material's true cost over the life cycle of its design. Now, today, because we have limited time, we're just going to look at the three-edge bearing analysis option. The three-edge bearing analysis is based off the indirect design procedure for concrete pipe. If we were to look at the different indirect design tiers, you typically start with your hand calculations using our concrete pipe design manual. These are all based off AASHTO LRFD equations that we use within our indirect design method. The next level is PipePac application. So we can put in project-specific variables for several different fill heights and identify which class of pipe we need for that project. Now, the quickest and easiest for most people would be this fill height table option. If you begin to use PipePac enough, you'll find that you can complete a design on PipePac just as quick as it takes to find a fill height table online and look up your certain parameters. It really is that easy, and you can go through quickly. Like I said, as long as you have an internet connection. So Kim, we're going to launch our first poll question.
Okay, give me just 1 second. I'll get that launched. Okay, everybody should be able to see that now. And the question is, to what extent have you used PipePac in the past? And you can check all that apply. The answer choices are every day for planning and design. Only when I have unique loading applications like low cover or surcharge loads, or I have used it to analyze the existing pipe experiencing loads outside the plant, or I've never used PipePac at all. So that's your options. Okay, I'm going to share those with the group. And Corey, the answers that you got out of that was 4% use it every day, 16% use it for unique loading applications, 8% use it for existing pipe conditions that they're trying to confirm, and 82% have never used it. So this is a great training webinar then.
Yeah, that's about what I would expect. I feel like when I've used it over the past couple of years, it's been more existing or near the end of a project planning phase. So some of the typical applications are just those. When you're completing a design in the planning phases, want to know what your class of pipe is. This is obviously where we'd recommend it to get ahead of it, both for culverts, storm, and sanitary sewers. It can also be used to value design projects. So if you know what your installation type is, you can actually engineer that pipe class for the specific installation. And then we can also analyze existing projects with some expected changes in the loading. One of the things I'd like to hear is what some of those unique loading applications, if there's any unique applications you've used PipePac for. So for that 8% or whatever it was, if you want to sound off in the chat and let us know some of those unique loading applications, that'd be great. So as I mentioned, we're using this for the indirect design method and classes of pipe. What we're really looking for is the class of pipe that can be designed and then tested for in the plant And that's according to the RCP pipe classes for a 0.01 inch crack per our ASTM C76 manufacturing standards. So if you're not familiar with the classes of pipe, we start with a strong pipe in class 1, and then we exponentially work our way up to an extremely strong pipe with a class 5. You can see the different loads associated with each class of pipe and its designation. So the only thing really changing in the manufacturing process is the addition of extra steel. Okay, so for the actual program itself, we have 4 different tabs that we rely on. Our pipe information, our load and installation criteria and more project specifics, the factor of safety for our deload tests, and our results. So starting with pipe information, this is what the actual application looks like. You have several different options for pipe shape, pipe type, wall thicknesses, and then inner diameter, which is based on your hydraulic results. So the most common is our circular pipe, which is a typical round pipe. These are based off ASTM C76 as a default entries for both reinforced and C14 for non-reinforced. So our inner diameters are set to 12 inch through 120 inch according to those ASTM C76 classes. So 12, 15, 18 all come stock within the program. And then for non-reinforced, they range from 4 inch to 36 inch. It also comes pre-programmed with our manufacturing A, B, and C walls. These are dependent on what the manufacturer actually has in their plants. Typically, it's a B or C wall. If you are a consulting or engineer at an agency, I always recommend just asking the manufacturer what they have in their plant for the actual forms and manufacturing processes. Now, non-reinforced can also be set to those ABC walls, or you can kind of customize it with the user input. The other pipe shapes available are vertical elliptical and horizontal elliptical. These could be used if you have certain trench limitations or vertical clearance issues. And then also our arch pipe shape. Now, once again, there's pre-programmed shapes within PipePac for these dependent on your ASTM C507 or 506. So you would put in your span and it will automatically populate the rise and the wall thickness for you. So once you have your pipe information in, you can take a look at the load and installation criteria. As I mentioned, this is where you enter in the majority of your project specifics. So you have your soil types, you can enter in any vertical surcharge loads that might be there, fluid load, live loads, and then your installation criteria. Now, if you're familiar with PipePac, you know you can do some pretty unique stuff with the vertical surcharges. In a recent design I helped with, we were looking at having one of these crane loads on top of a temporary drainage structure. So this crane was going to be loaded in place and was going to be there for several months. And we looked at the ground bearing pressure, converted that to a surcharge load, and then incorporated that into our PipePac application as a surcharge load. One of the other unique examples I got was out of Utah, sent over by Randy Wallen. It was an existing 42-inch RCP class 3 with 17 feet of fill. And after 10 years or so, a developer added an additional 15 feet of fill, as you can see to the roundabout, with some waterfalls and other large rocks. Didn't tell the sewer district, and once they ran the PipePac application, they realized they might be in trouble and might be overloading this existing pipe that was under the ground. Luckily, they ran some cameras through it, didn't find any longitudinal cracking. Turned out the pipe was fine, and that's one of the benefits of using concrete pipe is the increased loading capabilities. But we do also recommend, if you're going to load an extra 15 feet of fill over an existing pipe, have one of the manufacturers run some designs, run your own designs, and make sure to video the pipe afterwards. Now for height of fill, we have 4 different options we input. First is your minimum fill, which is exactly that, and our maximum fill. So minimum and maximum fill heights you expect. And we also have incremental fill options. Essentially, you can run the PipePac program and develop fill height tables based off of those incremental fills. So in this situation, we have a min fill of 1 foot, maximum of 20, and incremental fills at 1 foot. So PipePac's going to look at 1 foot, 2 foot, 3 foot, etc., all the way up to 20 feet. And then for a selected depth, this is just what will be highlighted in the program. It doesn't actually control anything. So I know I've had users that have used 0 feet and they wonder if that has any implications on the actual design itself. It doesn't. This is just what's highlighted in your results. So the selected depth isn't necessary to the design. It'll just help highlight what's in there. Several different live load options exist. AASHTO trucks, Cooper E80 loading, aircraft loading, Canadian Highway Bridge Design Codes, our other, which is a customizable option, and then of course none. Now with that, we do have several customizations available with each of these live load types. So once you choose one, say AASHTO for instance, you're then brought to a separate screen with the live load parameters. So in this situation, we have a single axle load, which is our AASHTO HS20 truck, a double axle load, which is our tandem loading. And together, that's what makes up our HL93 live loads for our AASHTO LRFD designs. Now you can also customize either of those. You could input your own single axle loading or your load per axle on your double axles. And then you also have the options to input your default impact factors. Now moving over to the installations, you have the option to choose which installation type you want to use. We typically use the positive projecting embankment because that is the most conservative, but each of these installation types have different frictional forces working in the pipe soil structure interaction. So each of these does create unique loading for the pipe and controls the earth load. So trench is typically the least amount of earth load. With your positive projecting, you typically have the most frictional forces weighing down, creating the higher earth loads on top of the pipe. And yes, this was the most up-to-date picture I could find of these installation types. Now for the bedding type itself, this is how we derive our bedding factors and vertical arching factors. You do have the option of using the old Marston B and C beddings. This is a variable bedding factor that is dependent on your trench width, your depth, and your materials used. This is somewhat of an outdated and obsolete method of evaluating. We do have new research with our standard trench and embankment installations. So our type 1 through 4 installations, which I would recommend using. And with these installation types, we can see how each installation type with its specific materials and compaction percentages controls the strength needed from the pipe. So if you're familiar with the pipe structure interaction, the pipe soil structure interaction, excuse me, for our designs, a type 1 requires the most stringent installation requirements. So the best material with the highest compaction. So because of that, we don't need as strong of a pipe. Now a type 4 is the opposite, where we have almost no material or compaction requirements. So we're almost relying completely on the pipe itself to provide that strength for the soil structure interaction. Now we look at type 2 and type 3, linearly progressing through those, requiring both some strength from the pipe and some strength from the installation itself. So with that, we have our second poll question, Kim.
Okay, you bet. Let me launch that. All right, so everybody should be able to see that and be able to answer. Which installation type and bedding factor requires the strongest concrete pipe? Standard type 2 trench, type 1 negative embankment, type 1 trench, type 4 positive embankment, or not enough information? This is a tricky one, Corey. Everybody's taking a little bit longer to answer, so I'll give everybody just a minute or two more. All right, let me share those results. So Corey, we had 3% say type 2 trench, 14% said type 1 negative embankment, 9% type 1 trench, 57% said type 4 positive embankment, and 17% said not enough information. What's your thoughts on that?
Assuming everything is the same with the fill heights and loading criteria, it would be our embankment with the type 4 installation. Because that type 4 installation, as I mentioned, is essentially throwing the pipe in the ground. You're relying with the majority of the strength coming from the pipe itself. So for that 50% or so, good job. Okay, so factor of safety. We have our factor of safety inputs from ACMC 76 standard. I would recommend leaving those as is. That's what our indirect design is based off. It's basically saying our service load is at our 0.01 inch crack, and for 2,000 pounds per foot deload, we have a 50% higher ultimate load. And then for 3,000 pounds per foot and over, we have a 25% higher ultimate load. You do have the option to specify your own, but I don't think I've ever customized this. I typically use it as the ACMC 76 standard. And then finally, we have the results, which is pretty easy. You just click the Analyze button, and then it will tell you for your type 2, type 3 installation, because that's what we chose, what your class of pipe needs to be. Now, as you see, the height of fill for the selected depth is 10 feet. That's really the only portion that our selected depth option comes into play. Once we click on the preview analysis, though, we can get a full report of the entire loading for our deload summary. So this is at that bedding type 2, and we can see the arching factors, earth loads, live loads, surcharge loads, and total loads. It then gives us our bedding factors and the required deload to meet that pipe depth and installation type. If we wanted a little less information, we could run this as the summary. This is where we essentially have our fill height table set. So at each pipe depth and each type, it gives us which class of pipe is recommended for that situation. Now, one quick note, we do have a PipePac help menu. If you were to click help and then download the manual here, it brings up a 103-page manual that has a ton of information on each variable, which options to choose, not only for the 3H bearing, but for the LCA and the CAPE programs also. Okay, so to run through a quick case study, this was a recent project I helped with, and I got this bid item to install a 60-inch irrigation pipe crossing. They specified a class 5 at 5 to 10 depth, so 5 to 10 feet of fill height, and using an APWA ODOT trench detail. So when I ran this, I assumed a B-wall 60-inch RCP. I also assumed 120 pounds per cubic feet and a fluid load. I used my fill height from 5 to 10 feet. and a positive projecting abatement, since that is the most conservative case. And the ODOT trench detail, Oregon DOT, is similar to a type 2 installation. So that's what I'm going to use for my actual bedding materials. And then of course I followed ASTM C76. So what I really wanted to do was check with these given parameters, could we value engineer this class 5 RCP and use something more appropriate for the given bedding type. So heading over to pipepac.org, I'm going to launch a video. Let's see. I'm going to launch a video that will take us through this example. In this example, we will imagine a design engineer is evaluating the use of a class 5 60-inch RCP with varying fill from 5 to 10 feet. The engineer wants to optimize the strength of pipe for the required type 2 installation utilizing ACPA's PipePac. To perform this evaluation, we first open the PipePac web application. Once we've got to the home screen, we have the option either to choose help and look at the actual processes involved in the application, or we can proceed to the PipePac application. Once we've done that, we have two options, either create a project or load an existing project file. For this situation, we are going to create a project. For this, we're going to use a title of example webinar. Skip everything else other than country US and analyzed by C. Fraser. And then we'll create a project. From here, we have three options. We can either choose 3-edge bearing analysis, cost analysis of pipe envelope, or life cycle analysis. To investigate the classes of pipe, we choose 3-edge bearing analysis. Now we need to develop an alternative name description before we proceed. For this example, I use 60-inch RCP example as my alternative, and I'll select US customary units and ASTM AASHTO standards. Now that we have a project description in place, we can start to fill in our pipe information. We'll take a look back at our project specifics, 60-inch diameter reinforced concrete pipe. We'll use this to enter in our pipe shape, pipe type, wall thickness, and inner diameter. So we start with the circular pipe shape, reinforced pipe type. We're going to choose a B wall for this application. If you are in the consulting world or an engineer at an agency, you can contact your local manufacturer to see what wall thicknesses they use with their machinery. For the inner diameters, the ASTM C76 inner diameters are already entered in that you can select from a drop-down menu. We'll choose our 60-inch diameter and move on to our load installations. Once at our load and installations, we can input our project specific variables. If we take a look back at what those are, we're under 5 to 10 feet of fill, a positive projecting embankment installation type with a type 2 bedding and highway live loading. So running through our variables, we'll keep our soil type as 120 pounds per cubic feet. We do not have a vertical surcharge. We will include the fluid load. And for our live load type, we're going to use our ACPA truck. And once we click on our ACPA truck, it brings up our live load parameters, which gives us two different trucks, our ACPA HS20 with 32 kips per axle, and our double axle, which is our ACPA tandem axle. Combined, these make our ACPA LRFD HL93 live loads. If we wanted to, we could increase this single axle load to 40 kips, which would give us our ACPA HS25. But in this situation, we just want to use our default HL93 live loading. And once we have that input, we can close out and then enter in our height of fill. We are going from 5 feet minimum fill to a maximum of 10 feet with 1 foot increments. And we're going to use a selected depth at 6 feet. For the installation type, we're using a positive projecting embankment. This gives us several different parameters which would be used if we were using the traditional Marson Spangler bedding. Now, if you remember, we were looking at optimizing for a type 2 bedding installation. I'm also going to use a type 3 bedding just to compare. We don't have to worry about grouted, non-grouted. That's for jacked and tunneled applications. And selecting the standard installation will choose a bedding factor and vertical arching factor for us. Now I move on to our factor of safety tab. Here we have specified our ASTM C76 standard, which constitutes our 0.01 inch crack as our service load with an additional 50% increase in loading for our ultimate load. You do have the ability to specify unique factors of safety. We're going to stick to the ASTM C76 standards. Finally, we can take a look at the results. Now you see our height of fill at our selected depth is 6 feet, and all we have to do is click here to analyze. And once we do that, the program runs itself and analyzes the conditions we input. You can see here that at each selected depth, it gives us the class of pipe required for that situation based on our installation bedding type we've selected. If we wanted more information, we could select preview analysis. The preview analysis report gives us results for the specific inputs. And we can check that on this report looking at our pipe data, installation conditions, and loading. It then gives us different charts that we can look at both for our type 2 bedding and type 3 and any other bedding type we might have chosen. So for this bedding type 2, it gives us a look at what's happening from 5 feet to 10 feet depending on the increments we put in. It shows our earth loads, live loads, total loads, bedding factors, and then the required deload for each loading application. Now, if we didn't need as much information for the project or wanted to send someone less information, we could preview summary. Now this gives us the same pipe data and installation conditions, but it puts it into essentially a fill height table for easy reading purposes. So you can see we have our pipe depth, our type 2 installation, and type 3 installation, and we can match which class of pipe we need for each situation without any of the extra indirect design loading criteria listed like we had on the report itself. Now, once we have this information, I'll typically save this either using the save as or print function. Print it off to a certain location, then I can send it off to owners, engineers, manufacturers, and so forth. So to go back to our original question, if we could optimize this design, let's take a look at what's happening from 5 feet down to 10 feet with our Type 2 installation. It looks like all we need is a Class 2 pipe for that entire situation. And even with a Type 3 installation, so a little less stringent installation requirements than the Type 2, we still only need a Class 3. So if I was presenting this to an engineer or an owner as the design engineer, I would offer to help save money for that owner a Class 3 pipe with the accompanying Type 2 bedding. And that could significantly save money depending on the length of the project for the owner. Okay, so quick note, I recommended a Type 2 installation, and it was noted that if a Type 3 bedding worked in that situation, why wouldn't we just recommend a Class 3 pipe with the Type 3 bedding, which you could if it was a private situation. I found that typically with agencies, when they're requesting an actual DOT trench detail, that we commonly stick with that, and that's why I recommend Class 3 bedding with the Type 2 bedding required by that DOT. So Kim, I think we had one more poll question.
Yep, let's launch this last one for this design app. Okay, so when considering the two apps that we talked about today, do you have any current projects that you could utilize one of these design apps? And I noted somebody did mention they could not click on this. So again, we mentioned it earlier in the webinar. If you're having trouble, resize your window. If you have it on full screen, if you resize that, it should allow you to click and select one of these.
Yeah, and while that's being filled out, just a quick note since we're running out of time, we do have handouts, our Design Data 1 and Design Data 9, which have live loading in Design Data 1 and our standard installation loading criteria and methodology in Design Data 9. So if you want more information on the actual design procedures for PipePac, or want increased knowledge of what's actually happening behind the scenes, those are two great resources, as well as the Concrete Pipe Design Manual, which can be found on our website, concretepipe.org, for free. And then we have several design and installation webinar tutorials on our YouTube channel. You just go to YouTube and search for American Concrete Pipe Association. You can bring up several webinars on design, installation, and some other goodies on there.
Yeah, so Corey, those handouts that Corey mentioned, you can find those right here on this webinar in your control panel. So you have different options. You have sharing webcam, audio, dashboard. On down the line, you'll see handouts, and there's two that have been loaded for this webinar. So if you'd like to download Design Data 1 or Design Data 9, those are there for your use. If you don't get to them right now during this webinar, as Corey mentioned, you can find those on our website at no charge. So good results on whether or not you have current projects. 14% have current projects going on that they may be using these apps for, so that's great news.
Oh, cool.
We have one more polling question, and then we'll be wrapping this up, and we can take some questions following the wrap up, because I know we are just about at our hour. So let's launch this final one. So how are you most likely to utilize these apps? During the design phase, most likely on your computer. Would you be using them in the field to confirm or modify your designs, or maybe you're not sure where you would use them yet? Okay, I'm gonna go ahead and close that up and share those results. It looks like the majority of folks would be using those during the design phase, most likely on the computer, which is great because PipePac is only a web-based internet required type application. So that'll work well for that. And then I do believe that our Compare Flow app, it works pretty good on your phone as long as you have a decently sized screen. So even if you are using it in the design phase, that should work well for you. Let me close this. And we just wanted to announce that our next webinar will be in August. So we do these every other month. And we'll be talking about innovations in concrete pipe in August. So be looking for an invitation from us sometime in July. We'll push that out to you. And if you don't get it, feel free to reach out to me. You can find my contact info on our website, concretepipe.org, and I'll be happy to make sure you get that. Now, I do want to wrap up with just a few final comments, and then we will answer. We have some great questions that came in. So Corey and I will stay on and get those answered. PDHs are available for this webinar. We do check attendance and make sure you are on a certain amount of time. And then we will send those out probably the end of this week or the beginning of next week. So if you'll be patient with us for those, we will be sending them out, but it takes a couple days with over 300 people to get certificates to everybody. And also this has been recorded. So if you have colleagues or you want to go back and review it, we do post it on our website and that link will get sent out to you. But if you're looking for it, just go on concretepipe.org under education and then webinars, ACPA webinars, you'll see it posted right there. So that's all we have for today. So I want to thank everybody for joining us. And again, we'll be staying on here for questions, but I do want to be respectful of everybody's time if you have to hop off. Thanks for joining us. Hope to see you in August. And we'll continue on from here with some of the great questions you guys had. First question, going back to Compare Flow with what Trig talked about. There was a question that said for long box culverts with a lot of joints, the end value should be higher than a 0.011. Now, if you remember, Trig talked a little bit about the fact that the lab value for concrete itself is a 0.01. However, we typically, for bins, turns, manholes, those types of things, including joints, will add 20 to 30% to that lab value for design. So we are typically using a 0.012 to a 0.013 to account for those type of items. Another question, I'm going to show one of Trig's slides to make it a little easier to understand. The question was about plastic pipe and whether or not the liner, I'm not sure if you guys can see my screen yet. Can you see that, Corey?
Yeah, I see it.
Okay, so the question was about plastic pipe, and if this was a smooth lined plastic pipe, shouldn't it have a lower, somewhere around 0.01? So as Trig had mentioned, this is a triple wall polypropylene pipe, so it does have a liner on the interior and the exterior. But over time, with loading that's seen on the pipe, almost 100% of the time, you're going to get corrugation growth. And so that's why we typically recommend for a plastic pipe, you would have a 0.15 to a 0.018 Manning's end value. Now, if you're looking at a PVC, something that's a solid wall, then yes, I would agree that typically does not show corrugations. And you could use more around the 0.011 value. Okay, that's all of that one. Let me get back to, let's see, get back to the question panel there. Another one from Trig's presentation was, is the culvert program based on HY8? And it is not. It is based on just the standard Manning's-N equation to calculate hydraulic flow capacities. So you're looking at a Manning's-N coefficient. You're looking at all of those things that are in that Manning's-N equation to calculate with compare flow. And it does not, I don't know if that was your question or whether or not it communicated with HY8, but that it does not communicate or integrate into HY8. Another great question was whether or not compare flow would convert from cubic feet per second to gallons per minute, and it does not. It does standardize that unit to CFS, but certainly, you know, if it were me, I would just, if I needed gallons per minute, I would take my answer and just go Google what the gallons per minute was. So that could be a solution for you on that one. Then on to yours. I think that's all I see on the compare flow. So Corey, over to you. Can PipePac be used for trenchless installation applications for determining pipe class requirements, excluding installation loads?
Excluding installation loads. So I'm assuming excluding the thrust forces from actual pushing applications of jacking. Yes, it can be. It does have jacking and tunneling as part of the installation requirements to evaluate for the class of pipe.
So yeah, I kicked that back to you, Corey, in case you needed to show the screen there.
Sure. Let me get.
While Corey's pulling that up, I can field the next question for you, Corey, if you want to show them where the jacking loads input is. But there was another good question about what bedding type would you recommend for flowable fill or lightweight cellular concrete fill? I would say that is going to be a customized installation. However, you could conservatively select a type 1 because actually a flowable fill would be above and beyond a type 1 installation. But that's probably pretty close if you want to use that for flowable fill.
Yeah, I'd agree with that.
Okay, did you want to just show quickly what the jacked or tunneled option is?
Yeah, it's just under installation type at the bottom. And once again, then you have the option under your bedding types to do a grouted or non-grouted, and that'll take into the consideration for the actual installation bedding when it's running through the design for your bedding factors.
Okay. When would you select to include or not include the fluid load in the analysis?
That's a good question. The new ASHO LRFDs have you include fluid load. It really doesn't make that big of a difference in smaller diameter pipe. It's once you start getting to the larger diameter where you're carrying a lot more fluid and it's increasing that load. But I typically always include it just to be conservative, even on 12-inch diameter pipe where it's not going to really make a huge impact to the actual design, but I almost always include it. I guess
Yeah, that's what I was going to say is conservatively, you can always include it. If you know for sure it's going to be more of a dry culvert,
yeah,
then you could not include it. Corey, someone wanted to know what your favorite pizza topping is.
Oh, that's a good question. You know what? I'm just classic pepperoni, but I do like pepperoni and jalapeno also. Those are my two go-to.
Corey grew up in Texas, so he likes jalapenos.
Yeah, yes.
Well, that actually concludes all the questions I see on here. So again, thank you guys for joining us. If you have any feedback for us, please let us know. We'd be happy to help. And we'll look forward to seeing you in August for innovations of concrete pipe.
Yeah,
Thanks, Corey.
real quick for everyone that's on, feel free to contact me if you have any specific questions. I'd be happy to help.
Yeah, so again, you can find myself, Trig, and Corey's contact info on our website under concretepipe.org. Just go to contact us. All right, have a great day, everybody.